seminar series number 7. Thanks for holding with us all these months. This is Christy Morris. I work for the National Park Service Air Resources Division in Denver. This, of course, is a seminar on different chapters of the TDep white paper, which is on science needs for a continued development of total nitrogen deposition budgets in the U.S. As I think all of you are aware, the paper and various articles in EM Magazine and Stoughton, as well as past webinars, are all available on the NADP website. If you look under the TDep Science Committee, you can find all of those there. So today we have 2 presenters. The first presentation will be by Graham Sexstone with the USGS here in Denver on snow and atmospheric deposition. And then following that, Greg Beachley from EPA will be giving us a presentation on remote sensory measurements. So with that, I think I can turn it over to you, Graham.
Great. Thanks very much, Christy. Can everyone hear me okay?
Yes.
Yep. Okay. Yeah, so my name is Graham Sexstone. I'm a research hydrologist with the USGS in Lakewood, Colorado. And today I'm going to be presenting on snow and atmospheric deposition, which was a chapter of the TDep Science Needs white paper. I just want to acknowledge all the authors that participated in the development of this chapter, which are shown on the screen. And let's see if I can advance my slides. So today, just a quick overview. I'll kind of want to just give a brief introduction about snow, its importance, and how snow and atmospheric deposition are closely related, and give an overview of current snow nitrogen deposition monitoring, and then really kind of highlight some of the future research needs related to snow and nitrogen deposition that we highlighted as a part of the white paper chapter. And I also wanted to give a brief overview of the Rocky Mountain Snowpack Chemistry Network, which is a project that I manage as a part of the USGS. So snow is the really important water resource, important component of the water budget in many regions throughout the United States, but it's especially important in mountainous ecosystems, particularly in the western United States, where it serves as really the primary source of water, the primary driver of much of the hydrology in this region. And because of that, it's tightly coupled with mountainous ecosystems. And nitrogen deposition in these areas has a lot of interactions with snow, because the snowpacks essentially serve as these natural water reservoirs where they accumulate in the fall, winter, and spring, and then generally melts during the spring and summer each year. So both wet and dry deposition of nitrogen are important to basically the chemical makeup of the snowpacks. And this figure is essentially a conceptual diagram of a lot of different processes that influence kind of highlight interactions between the snowpack and nitrogen deposition. So you have wet and dry deposition, falling on our snowpack, interacting with our snowpack, but then there's also our snow, especially in complex mountainous environments, undergoes a lot of physical interactions with wind exposure, as well as interactions with forest canopies and vegetation. And these interactions can have a really strong influence on the distribution of our snowpack in mountainous environments. And likewise, these interactions can physically redistribute the snow and change the snow, but also can chemically alter the amount of nitrogen in our snowpack. So we think that the initial wet and dry deposition are sort of, and that distribution is of greatest importance in terms of estimating our total nitrogen deposition in mountainous areas, especially related to snow. However, this spatial distribution of snow water equivalent and how the snow is changing throughout the season, both temporally and spatially, can also have a strong influence on how much nitrogen is stored in this snow reservoir. So this to highlight that, I've shown on here these two figures in the middle are some snow modeling that I've been working on in the Rio Grande Basin in southwestern Colorado. And so this top figure highlights the amount of winter precipitation falling in this mountainous region. And then the bottom figure highlights the peak snow water equivalent, so the amount of water stored in the snowpack at its maximum value. And note the scales are much different on these figures, so it's hard to do a direct comparison, but you can just get the idea of how different sort of the spatial distribution of these things look. And that can be important in terms of accurately estimating our total nitrogen deposition in these snow-dominated regions. Another important point is, when our snow melts, the input of nitrogen into the system is strongly impacted by preferential elution. And so essentially, this figure on the right, especially the bottom right, we can focus on nitrate, highlights where these transparent bars represent the concentration of nitrate in a snowpack towards the end of the season. And this line represents the change through time of snowmelt water nitrate concentration. So you see that initial pulse of water from the initial snowmelt can be highly concentrated, in this case up to 7 times greater than the concentration in the snowpack itself. So that process of preferential elution is really important in terms of how, what nitrogen concentrations are put into the system through time. So to give a quick overview of the different nitrogen deposition monitoring related to snow in wintertime, we can monitor the different phases of nitrogen deposition through wet deposition only, such as the NADP collectors, or dry deposition only, such as CastNet. And then there's also methods to put out bulk collectors, which essentially collect both wet and dry deposition. And then likewise, we can collect composite snowpack samples, which essentially serve as a large bulk collector where we can collect both the wet and dry deposition that fell on that snowpack. These different monitoring networks can also be used in conjunction with each other. So for instance, this photograph highlights the Dry Lake NADP site, and we also have a snowpack chemistry site where this photograph was taken from. And so we can utilize both of those measurements, and by differencing the two, snowpack representing the total deposition and NADP representing the wet component only, we can infer maybe the importance of dry deposition, where we have these sites located in conjunction with each other. And then in terms of dry deposition, we can use the ambient nitrogen air concentrations and model deposition velocities to come up with dry deposition estimates. So some of the future research needs that we highlighted as a part of this white paper, really were revolved around trying to improve understanding of processes that affect nitrogen deposition in these snow-covered environments, and how can we utilize that process understanding to potentially improve atmospheric deposition modeling. And so one of the key focuses for future research is, potentially trying to improve the existing measurements and methods that we have, such as, in the winter, collecting snow at NADP sites, for instance, can be challenging just because of, the extreme weather conditions, windy environments, and snow being particularly challenging, and having a low catch efficiency. So, considering putting windshields on collectors to help improve catch efficiency and also limit, potentially wind-blown snow from other areas being deposited into the buckets is kind of an idea of, improving our existing infrastructure. Other ideas are kind of adding auxiliary measurements at existing stations, such as collecting, bulk snow samples, or bulk collectors, putting them out in conjunction with NADP. That way, if there are equipment failures, or if it really just snows way too much for our collection buckets, we can have these kind of backup measurements that can be used to kind of fill in the gaps for those time periods. And also, as I mentioned earlier, try to utilize that comparison of total deposition observations with wet deposition observations to try to infer the dry deposition component. In addition to the sort of existing measurements, there's definitely a need for more spatially distributed measurements, and really to try to better understand the representativeness of our historical data. How representative are our monitoring sites of processes that occur, such as this wind redistribution of snow and the canopy effects that I mentioned earlier, and also sort of the big elevation gradients that we see in these mountainous environments. So there's been some efforts using bulk collectors and kind of a combination of using ion exchange resin collectors with bulk snow chemistry sampling that has been shown to be a potentially viable approach for some of these more spatially distributed campaigns. And we also kind of highlighted really the need for high elevation, particularly alpine monitoring. This really could help improve our understanding of the importance of elevation gradients and how we can kind of better estimate nitrogen deposition over these ranges of elevation by having these high elevation sites. And existing infrastructure, if it can be leveraged as much as possible for new data collection, would be best, just because of the challenge of setting up sites like that. Also highlighted just the need for improved understanding and potentially new research on the importance of the snow characteristics, such as snow surface roughness and the liquid water content of the snow surface in terms of its melting, and how that all interacts with dry deposition velocities. That's really a large uncertainty in atmospheric deposition modeling, and so studies to further evaluate that would be potentially really valuable, and maybe determine how much physically based snow modeling might need to be kind of incorporated into this atmospheric deposition modeling realm. Another real important uncertainty is sublimation, which is essentially analogous to evaporation, where it's directly snow to vapor or vapor to snow. And how that sublimation processes influence ion concentrations is a big uncertainty. and we don't really, and sublimation in places like Colorado, for instance, is a large component of the water budget. So that more research into those phase changes is definitely needed. And lastly, more research related to the ion exclusion, snowmelt chemistry type studies using lysimeters would really provide valuable data to be able to kind of validate studies looking at that snowmelt water concentration. So just really wanted to quickly highlight also our Rocky Mountain Snowpack Chemistry Monitoring Program. This is a long-term project that I run with the USGS. That's kind of a collaborative effort with the Forest Service, Park Service, State of Colorado, Teton Conservation District. And it's really kind of it's a network designed to monitor atmospheric deposition, but particularly at higher elevations and trying to fill in some of the gaps of the NADP network. The long-term project's been going since 1993, and we have 59 sites currently in the Rocky Mountain region. And so what we do is we essentially go out to these locations, and once a year, close to peak snow accumulation, we'll dig a snow pit. We'll analyze the physical properties of the snowpack, and then we'll collect a bulk sample of that entire snowpack. And essentially that represents a composite sample of all the deposition that occurred from when that snow started to accumulate, which is generally October or November, to when we collect the sample around March and April. And so then we kind of keep that sample frozen and return it to our lab for analysis each year. This is a sort of a map of the distribution of our snow chemistry sites in blue, and then the NADP sites are also shown on here in red. So you see we have pretty good spatial coverage throughout the Rocky Mountain region. This is a map from 2018, just highlighting how these data can be looked at to highlight the spatial variability. And this is dissolved inorganic nitrogen and concentrations on the left and deposition on the right from our snow chemistry data. 2018 was an interesting year. We had really low snow in the southern Rockies and very high snow in the northern Rockies. So you see this real big difference in concentrations that reflect that difference in snow year. But yeah, that's just kind of an example of the spatial extent of our data. And then these plots highlight the sort of the temporal variability that we've been seeing in nitrogen deposition. So these are all our data through time. And the trend lines represent different regions. So the pinkish red is the entire Rocky Mountain area. The green is the northern Rockies, the blue is the central Rockies, and the purple is the southern Rockies. And so we have nitrate on the left, ammonium in the middle, and then dissolved inorganic nitrogen, essentially these two combined, on the right. And so we're seeing pretty clear decreasing trends in nitrate concentration and deposition, statistically significant in all regions. The ammonium is increasing, statistically significantly increasing in all of the regions except for the northern region, both concentration and deposition. And then the DIN is statistically significantly decreasing in all regions except for the central region that is kind of showing the highest increases in ammonium. And this is something I've been working on recently, as I kind of mentioned, looking, and it's sort of a follow-up on a study that Dave Clow did many years ago, but now we have a lot more data and trying to look at these sites where we have snow chemistry data at NADP gauges. And so we're trying to look at, kind of the comparisons. So these are 3 different sites where we have these co-located observations. And you can see nitrate and sulfate and ammonium, for instance, compare quite well between these observations. We have snowpack chemistry on the x-axis and NADP on the y-axis. Whereas, some of these other ions, like base cations, are really weighted more towards the snow chemistry, and it's highlighting the importance of the dry deposition component. Another interesting thing with this type of analysis is we could look at sort of the differences in elevation between sites. For instance, this Apgar Lookout snow site and then the Glacier National Park NADP site are, 2 kilometers away from each other, but they're 2,000 feet in elevation difference. And we see, particularly ammonium doesn't have as strong of a correlation. And so this type of comparison can also potentially start to help with looking at the influence of elevation, which is quite important for, snowfall and SWE distribution differences. So yeah, I'd encourage you to check out our webpage and use our data if it's of interest. I'm always interested and happy to collaborate with these data. So that's what I had. Thanks for listening, and happy to answer any questions.
Thank you, Graham. Appreciate your presentation. Does anybody have a question for Graham? Go ahead and unmute yourself and ask away. If nobody else has a question, Graham, can you tell us a little bit about your organic nitrogen analysis that you've done in Snowpack? I know Katie Benedict gave a talk recently that sort of questioned some of those measurements, and I just thought maybe you could tell us a little more about that.
Yeah, I haven't dug into those data too much. We've essentially started to, analyze total nitrogen, and that would include the organic nitrogen component. And then essentially we can difference the total nitrogen from the dissolved inorganic nitrogen values and try to come up with that organic nitrogen piece. I haven't really dug too, like I mentioned, I haven't dug too much into those data. I did look at them briefly, and it looked like there was quite a bit of noise in the data. So that might sort of speak to the analytical precision. And it's also, I guess, I also have concerns about the importance of needles and leaf litter in those data. We definitely, from when we melt our snowpack chemistry samples, you do often get vegetation in the bag. So yeah, I think that could be an important influence. But I'd love to hear more about. I missed what Katie presented, so I would love to hear more about what she had to say.
Yeah, and I was just looking to see if she was on today, and I don't see that she is, but let's plan a follow-up conversation on that, because I know we were all hopeful that Snowpack could give us a good number for that. So
yeah,
very good. Does anybody else have a question for Graham?
Yeah, Graham, this is Mike Bell. Can you go back to the long-term plots that you had put up?
Yep.
It's about the ammonia concentration and deposition decreasing in the Northern Rockies versus the other. And I think the others follow the general trend that we think about of ammonia increasing. Is you think it's just because it's northern latitudes and maybe the farming season is shorter there and thus not getting into the snow as much?
Yeah, it's definitely an interesting trend, and I think that's a good idea that maybe it is a function of those northern latitudes. It's also just based on the logistical challenges of sampling the network. We often we go to the north first, essentially. It seems a little counterintuitive, but there are lower elevations generally in the Northern Rockies. So we can make the southern rocky sites last longer. And so we're, I don't know if that plays into it at all. Like we're potentially sampling earlier winter there than some of the other regions. But it did seem like earlier in the period, the Northern Rockies was following a more similar trend to the other regions and diverged. So yeah, it's definitely an interesting change.
Yeah, I'm curious if the NADP wet deposition data around there is similar.
Right.
Check some of our conditions and trends pages and see what's happening in those parks.
Hi, this is Jill Barron. I've got a question.
Hey, Joe.
Hello. One of the greatest sources of uncertainty is just measuring volume of rain. And you had a long list of things that could be done, improve, more research to get that better numbers. But remote sensing wasn't one of those. Is there any talk about trying to get a better idea of just how much snow falls using remote sensing and then marrying it to the chemistry measurements that you proposed?
Yeah, I mean, I think a lot of what I focus my time on is more on the physical snow hydrology side of things, and that is the biggest kind of science question, is just trying to come up with better spatially distributed estimates of snow water equivalent. And kind of what tried to hit home at the beginning is there's a lot of uncertainty in just us understanding how much snow is out there. And so, yeah, I think the remote sensing side of things, there's a lot of up and coming technologies. Our best remote sensing data right now is snow covered area in terms of a snow measurement. We don't really have a good way to directly measure snow water equivalent yet from remote sensing. At least from satellite-based remote sensing. There's sort of airborne techniques, such as the NASA Airborne Snow Observatory, where we can use LiDAR to get really nice, spatial pictures of how much snow is out there. But those are they're not available everywhere, and they're certainly cost prohibitive. So I see that as a huge challenge, and from a lot of the work that I'm doing, I find that really the best approach is going to be trying to combine measurements, remote sensing, and spatially distributed snow modeling. It's going to be our best bet at coming up with better snow estimates. It's kind of utilizing, no one technique is going to solve that question. But I think having that spatially distributed snow amount would be huge for deposition estimates, and it's a really important piece.
And maybe we need to make a lot more noise about asking the remote sensing community to give us have them figure it out.
Yeah, well, there's a lot of noise being made from other communities about that for sure. It's one of the grand challenges, at least in the snow hydrology world.
If there's,
Thanks.
Yeah, thanks, Jill. If there's not another question, I'll ask another. Graham, can you show your slide of the snowpack versus NADP concentrations?
Yep.
And it looks like there that the results were similar to what Clow published many years ago with a shorter record, meaning that the comparison between nitrate, sulfate, and ammonium were very good. Was ammonium not significantly different as well?
I haven't run the statistics yet. I kind of just plot together this week.
Yeah.
But yeah, from visually inspecting it, So I basically pulled these together for a lot of different permutations of sites, and so not always the sites that are right next to each other. But when we look at the sites that have a pretty close proximity, less than a few kilometers, as long as there's not a huge elevation range, then they tend to compare fairly well. I would imagine, they would be not statistically significantly different. I think there's a lot more we could try to dig into with this, though, especially more so on, sites that are in close proximity but different elevations, or potentially influenced by different air sheds, that kind of thing. So that's something we're actively working on, really trying to, I see the snow chemistry as potentially having a really important capability of looking at that elevation range, because most of the snow chemistry sites are higher elevation than our NADP sites. I mean, there's certainly exceptions, like the Lockvale site, for instance, which is shown here. But we have a lot more high elevation sites that could be kind of looked at in conjunction with NADP.
Right, and this comparison and data have been so important in validating, the concentrations that we see at the NADP sites, just because there's questions about how much snow, is the bucket collecting, and so this data shows that it is a representative estimate of concentration at those sites, which is great.
Yeah, and I will say that my next step is to look at this. These are concentrations, and those seem to compare very well. I think the next step will be to look at deposition, which actually accounts for the snow water equivalent on the ground. And I suspect those might be more different, just because of the challenges of measuring precipitation in the winter, and then also how the snowpack evolves and sublimation processes. So I think that will be an interesting part of this comparison as well.
That's right. Are there any other questions for Graham?
Yeah, I got one. This is Greg.
Hey, Greg.
Hey, I looked at your map. This is the first time I ever thought about this, but your map that showed where your locations are in relation to the NADP sites, and what jumped out at me was the fact that TDep is trying to get at uncertainty in the TDep products, which everyone knows are model measurement fusion data product that involves a lot of interpolation of ground-based measurements, like the NADP measurements, for example. And what jumped out at me was, I wonder if anyone's ever done this, and if not, I'm sure that Christie's shop is going to want to fund this. And that is, take the TDep grids and/or the NADP deposition grids, but the TDep grid I think would be more appropriate, and sample those grids at your locations, but you want to sample them only for the snowpack period, of course, and the TDep product is an annual product, so you'd have to do things a little bit differently, I guess. But if you could take your data at your locations and take the interpolated, the TDep estimated value for the grid cell that contains your snow pit, then you could have, I think, a way of comparing the measurement model fusion product to a ground-based measurement, and so and thereby start to get at maybe not variability, but at least bias for these high altitude areas. So does that make sense?
Absolutely. I think it's a great idea.
Hey, Greg, this is Mike Bell. We actually funded Lior Ananis, who's also on this call, to evaluate TDep versus, like, the 2-year agreement, first year is looking at TDep versus IER samplers. And our intent with the second year was to kind of move east and do some additional analyses. And that sounds like a great, very functional opportunity for that. So we potentially have everything lined up for that. So we'll have to work with Greg Beachley figuring out if we can get the monthly or the winter summations to do that. But that sounds, yeah, fantastic.
Yeah, you could.
Yeah, I agree. This is Leora.
Yeah,
I agree with that.
you could also take your snow depths that you measured and compare that to Prism, I guess. You know, I don't know if that's ever been done to try to, because that's a part of, you know, the NADP deposition estimate is the Prism grid, and so that might be another validation step to compare your snowpack depths to, you know, to the Prism grids. Anyway.
Yeah, that's a great idea. And I mean, part of that analysis would need to be the beginning of the snow season, which changes from year to year. So like, when does that snow start to accumulate? And I've been doing some work for those comparison plots that I've pulled together, you know, using SNOTEL data that's in close proximity, essentially time stamping when SNOTEL gauges start to show snow accumulation, and then kind of marking those as like, okay, here's our starting point for our sample. And then when we sample the snow, that's our end point. And that would be important information for that sort of comparison.
Right. Yep. All right. Cool.
Yeah.
Just a quick follow-up. One thing that builds off this is Leora. In the greater Yellowstone area, we incorporated the snowpack data in our sort of enhanced TDep estimates. And that was in a paper that was published in 2017.
Graham, there is also a question in the chat. Welcome, Van Bauer Socks. Would you like to ask your question, or would you like me to read your question? Van, I don't hear you, so I'm going to go ahead and read it. So from Van Bauer Stocks, it's obvious from the plots comparing co-located SNOTEL and NADP data that the sulfate agreement is much better than the nitrogen agreement. You speculated that the nitrogen differences could be explained by dry deposition. Have you been able to determine whether the nitrogen differences are stoichiometrically due to dry deposition of ammonium nitrate?
Yeah, that's a tough question. I haven't really started to dig into it too much, apart from just pulling these preliminary plots together. So that's you know, a good avenue to look into further going forward. Or if I mean, there's a lot of experts on the phone, so if anyone else wants to chime in, I welcome that.
Hearing none, I think we will go ahead and move on. Thank you, Graham, for your presentation. Appreciate it. Next up, Greg Beachley, and we'll get that switched up here.
And as we're switching over, I just want to apologize for all the emails and the confusion over the last couple of days. Having this many people on the invite, my computer was trying to check everyone's schedules against it, and it kept like slowing things down, and I pushed the wrong buttons, and then there was a Teams meeting, and then it was all day, and then it was back. And so yeah, thanks, sir. I'm glad you all made it. It's all you.
And just, I think moving forward, Mike and I decided to go ahead and keep this webinar on GoToMeetings. We have 2 more months after this, so we'll just continue with using this platform for now. All right, Greg.
Okay, can you guys hear me?
Yes.
Yes, okay. And then can you see the slide in presentation mode?
Yes.
Okay, so I think I'm ready to go here. Okay, so yes, thanks. So this is the satellite measurements chapter of the TDep white paper. And we're looking at oxidized and reduced nitrogen and how satellite measurements apply to reactive nitrogen budgets. I'd like to, well, I'm Greg Beachley. I'm from US EPA, Office of Air Programs. I'd like to acknowledge Daniel Tong, who's a co-author on the section with me, and also Mark Shepard from Environment and Climate Change Canada, who provided invaluable reviews and also gave a satellite-related presentation in at the TDep agricultural workshop this fall in Boulder, and I've used a lot of his slides. And also Kang Sun from University at Buffalo, and he also gave a presentation at that workshop, and I've also included some of his slides. So the satellites, I found this nice image from NASA headquarters here, which shows the current missions. Some of these have the, the atmospheric trace gassing instruments on them that we'll talk about. The RI satellite here has OMI and SWOMI and NPP. I probably pronounced that wrong, but has the CRIS satellite, CRIS instrument that we'll talk about. So the EPA disclaimer, what I say is not necessarily what EPA says. And Christy already gave a pretty good intro to the white paper effort. It's an NADP TDep report, and we're looking to describe the total deposition fields. We're looking at knowledge gaps and research needs. So from the satellite perspective, there's a lot of material on satellites. It was very hard to kind of boil all this down, and I was a lead author for this chapter, but I'm not really a real satellite buff. I've just kind of started dabbling in working with the data. So my strategy was really to conduct a research review and cover the basics of how the technique works, some of the planned improvements, and then really kind of go into studies and how they've applied that data set and those techniques to quantify surface concentrations, emissions, and deposition, and we'll go over some of the research needs. And I also included some of the materials I mentioned before from that agricultural TDep workshop, which I thought was particularly relevant. So just a quick background, how do satellites measure surface concentrations? This is kind of the first thing. We've got the satellite, the instrument is on board, the orbiting satellite. So OMI, TRPOMI, ozone monitoring instrument, troposphere monitoring instrument are aboard satellites such as that orbit the Earth, and they're above the atmosphere, so they're traveling over the Earth and orbiting. The sun's radiation comes in, it is reflected, and the satellite measures this incident radiation, this radiation here, spectral radiance, which is kind of a product of all the stuff that's going on in this vertical column. So what's going on, the optically active atmospheric trace gases that we're trying to measure, they're emitting, they're okay, so our vertical column here, and so we're looking down this vertical column, and we're really interested in this boundary layer. So someone explained to me as like looking down inside a glass of water and trying to understand what the concentration level is in this boundary layer. And a glass of water is a simple example because it's well mixed. The vertical column mixing ratios are variable, not uniformly mixed. So you've got these vertical profiles, and you really can't read a satellite presentation without the vertical profiles. This is concentration on the x-axis and altitude. Here's one of the ozone layer, which is not an optimal analyte for satellite analysis because it's got this big layer of ozone blocking its target down here. whereas ammonia is short-lived and has low background levels and is concentrated in the lower levels of the atmosphere. So this is a better vertical profile for satellite measurement. And this is a cross-track infrared sounder for ammonia. We've got this a priori vertical profile. So this is like all the prior information that's mentioned up here in the mixing ratios and is used as bounds and fed into a radiative transfer algorithm. And that spits out the applicable data product. So that's the retrieval. And that's what we is used to work with. So one thing I did want to mention here right before we kind of dive into the applications is the polar orbit. So you can see here's the orbit of the satellite. It goes from pole to pole. As the Earth spins, there's different transects or coverage. So what happens is the orbit is usually sun synchronous, and there'll be a local overpass time each day. So we're talking a daily measurement for Omi and for Chris. The ones that we're focusing on here, that's about 1:30 in the afternoon. This is a pretty significant factor because, thinking about diurnal profiles and optimum sensitivities, this is a good fit for ammonia. The TESS spectrometer, which is an earlier ammonia monitoring instrument, had an overpass at 9:30 with low morning ammonia concentrations and poor thermal contrast, so they had not as good sensitivity. And then the next alternative is this geostationary orbit. So this will be fixed over one location here, just like, let's just say Africa for this example. But this would then take scans, and this is what this movie is showing here. And then I've got this from the Tempo presentation from Kelly Chance, who's the Tempo PI. This is expected launch is in 2021. I'm not sure how long that will be delayed with our pandemic, but hopefully not too long. The nice thing is that this will have hourly scans, and with that we'll be able to get much more higher spatial resolution and temporal resolution. This will measure NO2, but unfortunately not ammonia. And so just to quickly, the satellite measurements are improving. There's better instrument sensitivity, spectral resolution. I've shown here the Omi. This is over Paris, France for Omi, and then Tropomi, and you can see the improved spectral resolution here. Also, the retrieval algorithms are improving over time. You can use the same data product, the same raw spectral signal, and rerun algorithms, so you can reprocess those to get better data as knowledge and technology advances. So the advantages of satellite data, it's the spatial coverage is really the big thing. You got data in remote inaccessible areas. You can find new sources. You can perform local and regional analysis with the same data set virtually. You can see pollution transport. This is helpful for source apportionment, dispersion, and deposition. Also, the long term. So these things are in orbit for long periods of time, usually around the order of decades. So this is really good for trends analysis. Also, conventional measurement biases, they're subject to their own uncertainties, but you don't have things like flow problems or inlet absorption. And then there's some limitations that need to be remembered. Not all pollutants are created equal. You can see some better than others, varying degrees of confidence for different species. They're affected by meteorology, so a cloud cover. Vertical resolution is somewhat limited for some species. We're kind of doing modeled correlations, or column densities can be affected by topography or sudden gradients. The temporal resolution is often sacrificed for an improvement in spatial quantification. We're looking at probably grids around 5 to 10 kilometers for optimal satellite data, and that's going to improve. But for now, that's about what we're working with, and it's typically less precise than monitoring. So the bottom line, what does this mean for deposition? The satellite-derived data sets are complementary, and the complementary to monitoring and modeling approaches. And you're going to hear this, everywhere you go. I went to a HACAS meeting, and this is the first thing they said: "We're not replacing the monitoring. We're not replacing the modeling. This is, meant to be used complementary." So these are the knowledge gaps from the white paper, and I'll kind of simplify these. The data assimilation of the satellite data, in the modeling can be used for model evaluation, the measurement model fusion. You can do extrapolation techniques. Also the land use information. Jill and Graham were talking about remote sensing of snowfall. So there's a lot of information like that that can be used in conjunction with, the trace gas sensing. To understand processes a little bit better. Another big use is the emission inventories. So there's a lot of uncertainty in the emission inventories, both for point sources and area sources, and satellites can be used to quantify that. And one of the near-term goals here is to participate in the, deposition scientists, particularly participate in these outreach communities. As a deposition scientist, you're probably not going to be able to, download a satellite data set and make heads or tails of it, but there's groups like HACAS that, really communicate the needs, will help you with your data needs, and then also kind of advocate for needed changes. So some of these long-term changes are more like, for the satellite scientist, improving sensitivities, the retrieval methods, the better characterization of the vertical profiles. And here's the HACAS website. So I keep mentioning HACAS, Health and Air Quality Applied Sciences team. I found them to be very responsive. I've obtained specialized data products from them. And they're always willing to answer questions. The site has links to tutorials and the tools and resources. So I encourage you to begin this if you're interested in looking at satellite data. And next, I mentioned the workshop, the ag workshop. So this was an agricultural nitrogen deposition focus workshop. There were 3 sessions focused on source apportionment, deposition models, emissions, and spatial and temporal patterns of deposition. And these are the presentations that were given from Kang Sun in regards to the emissions and lifetimes of reactive nitrogen, and Mark Shepard from Environment and Climate Change Canada, more of a direct application of satellite measurements to dry deposition measurements. And the discussion and the takeaways from this workshop were pretty consistent with the TDep knowledge gap. So we're talking data assimilation. Satellites have already played and will play a larger role in data assimilation for source apportionment models, deposition models, and then also in the measurement model fusion product. And with the emissions, everyone agreed that satellites will play a large role in improving estimates for emission inventories and finding new sources and quantifying sources that are hard to sample on the ground, for different reasons, but it's definitely a big use. So I want to get into some of the applications of the satellite data, and I've chosen some of these, kind of a highlight. Please look into the white paper chapter for a more comprehensive list of some of the past satellite studies that I've kind of reviewed. And the first, square one, is using satellite data. How do the satellite data derived surface concentrations compare with the actual surface measurements? So that's the big thing. If they don't compare well with surface measurements, then that's going to limit our use of them. In this paper from Lamsaw and 2008, was a big paper for nitrogen dioxide. And nitrogen dioxide is better validated and a more mature product than ammonia. Ammonia is quickly catching up, but for now, a lot of the work is focused on nitrogen dioxide. And Lamsaw compared the monthly OMI surface concentrations and to derive this, you're always using these models, you know, to get able to get these surface concentrations, and compared them with 5 different sites, APA, AQS, and Environment Canada's NAPS sites. So the results suggested a good comparability, a pretty good annual mean bias. They analyzed this for winter-spring differences, so seasonality. They found significant correlations and higher in urban areas, which makes sense for NO2. They used 2 different types of NO2 measurements, so that kind of showcases the issue of surface sampling bias with just traditional monitoring methods. And I thought this was also exemplary that surface measurement evaluations will help to characterize uncertainty. A lot of the the aspects that they looked at, regions, seasons, and different model parameters, averaging times, will affect the accuracy that you can get. And so moving on to ammonia, this is a snapshot from Mark Shepard's slide at the TDep workshop. So he showed this crisp ground level coverage here in Canada and in the continental US. And with the ammonia AMON sites for biweekly ammonia, and the NAPS sites, I guess it's 3-day ammonia. And this Fort Collins comparison snapshot here shows really good comparison. It looks like there's a little bit of a bias here in the winter months towards the measurements, but you can see that this is pretty good for 2 different 2 completely different ways of getting at surface concentrations. All of the studies showed pretty good correlation of 0.76, and actually the satellite showed a little bit more bias towards the satellite for all the sites. And there's more of these evaluations planned. And shifting topics here to emissions. So I mentioned the identification of the new sources, the emissions inventories. Emissions inventories range from more certain stack measurements from the EPA SEMS data to the less certain NEI, empirically driven, based on like emission factors and ratios. There's a lot of uncertainty, particularly with agricultural sources, but not limited to that, where satellites can be a lot of use to, really quantify, help to understand these emissions inventories better. And the methods that you're using, so there's this physical oversampling, which is basically, kind of averaging data cells at, 1 resolution and kind of concentrating to a smaller grid, helps to kind of focus the feature a little bit better that you're focusing on. So you can even look at point sources. And then there's rotating the wind fields and Gaussian plume decay fits. So it's like an exponentially modified Gaussian approach was used here in this study by Defoe and al., where they had really good correlation with these satellite-derived model emissions estimates versus actual EGU stack emissions. Another instance I'd like to highlight is this Whitburn et al. Study. So they use the satellite-derived concentration ratio. They're looking at time series of carbon monoxide and ammonia, and correlating that with, or I guess measuring the same occurrence of fire radiative power, which is also from satellites as well. In this case, MODIS. So I thought that was an interesting approach. And then this is a highlight from Kang Sun's presentation at the TDep workshop. So he showed satellite, a monthly satellite average data for Nebraska and North Dakota. This is IASI and this is Chris. You can see that these concentration profiles don't really line up very well with the NEI emissions for those states, and then there might be some reasons for that in terms of uncertainty, but the mismatch is pretty striking. And so what he had presented on was basically a deconvolution method, where he's finding an integrated mass enhancement. So using the emission impacted columns, vertical columns, that data, and then kind of subtracting that with the surrounding region of the unimpacted columns to get a signal minus background signal, this IME, and setting that to emission rates and lifetime of the pollutant. And then you use a conservative tracer and the length of the source region, and kind of use that for like a physical clearing out of the air parcel, and then you're able to simultaneously fit the emission rate and the lifetime for ammonia. And what his example that he reported got pretty good agreement here. Literature value was 35 to 88, and his calculated emission rate was 64 gigograms per year. This was for the ammonia in the Southern California basin. So that's an interesting strategy here. I did want to make a point. I'll quickly go through this because I'm going over here. But Schifferl and all used satellite and surface observations with the geochem, and they're able to analyze 5-year periods. We found that there's underestimation of ammonia around source regions. They found interannual variability. So this is kind of a really good example of how all these data sets are used together to really find answers that might be limited in other respects. Also, the study from Lonsdale used test data to reduce CMAQ model bias. Now, using satellite data, kind of directly to calculate reactive nitrogen deposition, and we're only focused here on dry deposition. So this is the data study from Carroll and all in 2018. And what they did is they used satellite OMI NO2 and CRIS ammonia. So that kind of represents the, it represents at least a portion of the oxidized nitrogen and the reduced nitrogen budget. Obviously it's a small part, at least in the case of nitrogen dioxide, but it does give you kind of a metric of that. And it will help to provide information on these compounds, which is, this is nice because the nitrogen dioxide is more of an urban component, whereas the ammonia, the reduced nitrogen, definitely has more of a rural signal, as I'm sure most of us are aware. So Mark Shepard actually went into this pretty detailed in his TDep ag workshop discussion, and some of these applications that he showed, I just kind of wanted to show as like something you can do with this dry deposition flux product. Here's the average basically taken from the last slide of the ammonia dry deposition flux for 5-year average, and then kind of the annual difference, the annual variation, interannual variability of ammonia, which is similar to what was reported on by Schifferl, that data assimilation study. And you can really see, the differences, especially here, this from forest fires in these years. And another aspect of this is you can, satellite data, you really can zero down on individual sources. So, here's an oil sands flux of nitrogen dioxide. Here's agriculture from the Central Valley. You could look at urban areas and really get a sense of what's going on in those areas. You can compare magnitudes for these different sources, and there's a lot of potential use for these products with a lot of these deposition studies. And then the last thing I wanted to mention here was the, here's the product from Carroll and all, the dry deposition flux, and here's a comparison with the TDep measurement model dry deposition. So this is ammonia. This is the other non-measured components, but it's primarily NO2. You can really see this urban influences really reflected in both. You get subtle differences. You see this big band of ammonia deposition here in Nebraska, Kansas, and northern Texas, and you see that in the TDep model, but not, this is more pronounced in the satellite and this is less. So there's differences, and I think that comparing and understanding these differences will help understand the processes, understanding the processes and the inherent uncertainties associated with the processes will really help to provide some answers on that. I think another step that I'd like to take on pretty soon, maybe soon after the measurement model fusion script conversion is done, is to incorporate these satellite measurements into the measurement model fusion process and see what we can do with that. So to recap, I went all over this stuff. Satellite is obviously, it's very fast moving field. There's a lot of players. Reiterate that the outreach groups do exist and very helpful to obtain products, assistance. That satellite data sets are complementary to monitoring and modeling techniques and lend themselves well to data assimilation and measurement model fusion approaches. Also source apportionment, model evaluation, and using all this information, we can learn a lot about processes, particularly like chemical transformation, meteorological effects. And you can look at both local and regional analyses. There's obviously applications that I showed to emissions inventories. So for future research, I think, continued progress on all this. I think there's been a lot of good work done, and, maybe some more characterization of uncertainties, some applications that maybe haven't been fully explored, like wet deposition or bidirectional fluxes for ammonia. And then obviously the geostationary satellite products, once those become available, that will definitely have a big influence on the field of deposition. So thank you, and there's just sources that I use, and there's a much more comprehensive list in the white paper chapter.
Thank you, Greg, and the deep dive that you took into the world of remote sensing for us. Does anybody have a question for Greg? There must be at least one question.
Unmuted.
Oh. Let's see.
All right,
Mike, yeah.
unmute everyone. Let's see if this will work.
Was that Selma?
I think it should. If you can try to unmute yourself, I think that should work. If I tried pushing the unmute all button, and some people are off now, so.
Is there an option in GoToMeeting to raise your hand, Mike? I'm not seeing that anymore.
Yeah, you can also put it in the chat if you have something and you can't unmute. Or maybe it was just the perfect presentation.
There's a lot of stuff to process.
Yeah, I think it's going to be really interesting to test out a lot of these remote sensing technologies against our maps, and like to use them to check and hopefully refine some of the uncertainty that we have moving forward once we have a better understanding of what it all means. It's going to be exciting.
Yeah, I really think there's a lot of application for a lot of this stuff, and I'm really scratching like the surface or the tip of the iceberg or whatever. There's so much information that you gotta kind of weed through. So, but yeah, I think it's a great tool.
Okay, if there are no other questions, thank you, Greg, for your presentation, and thanks again to Graham. let's see, our next TDep seminar date is July 15th. And on that day, we have Melissa Pachowski with EPA presenting on spatial variability of ammonia. So far, I just have one talk for next month. And then we have 2 more talks in August, and that will wrap up this series. So again, thanks for hanging with us, and thanks to our speakers, and have a great day. We'll talk to you next time.
Thank you.
You're welcome.
Christy.
Yeah.